when early on. But still this remains true. So there are quite a few things that we can learn from this definition of demand response. It starts with changes in electric use or usage, which is referring to changes in the usage by the end customers. And why is this change required? This is in response to changes in prices, because the price of electricity changes depending upon the demand and supply, hence the price for hence the changes in the behavior is necessary. This is done via incentive payments, which means a process or a mechanism implemented by a utility company to provide some form of incentives for the customers so that they can bring about this behavior, this change in behavior. And this is necessary to ensure system reliability. If there was unlimited supply of power, we would not need this mechanism. But because the power supply is limited and we are limited by the capacity of our power generators, we have to ensure that the demand is met within the supply bounds. So that's why demand response system is implemented, to ensure that the reliability of the system is not jeopardized. On the right side you can see an example of a dryer, clothes dryer connected to a smart switch used in a smart grid. Later on during the presentation I will talk about DLC, which is a way in which machines or appliances can be remotely controlled or switched off by the utility provider to ensure system reliability. So, demand response promotes interaction and responsiveness from customers. Interaction in the form of two-way communication and responsiveness in the form of accepting or rejecting the offer or the incentives made by the utility companies to the end consumers. What is the short-term impact of demand response? So, demand response has short-term impact and long-term impact. So, let us see what is the short-term impact. By short-term, we can determine the demand, and which can lead to economic benefits to customers and utilities. So, having a short-term having demand response program in place ensures that the utility knows what is going to be the demand and can ensure appropriate supply. Further, if the supply cannot be met as per the demand, utilities can then provide some incentive payments to ensure that customers are benefited and they can change their behavior, and utilities are benefited because they can manage the consumers within their capacity. What are the long-term impacts of demand response? The long-term impact is to ensure that we reduce peak demand, and this is achieved by bringing about a change in the customer behavior. Once initially you start with a short-term solutions, and eventually the final aim is to ensure that a change is a behavioral change is brought about within the customers' consumption habits. So, we want to change the habit of the customer in the long run, so that we do not have periods of peak demand, and this reduces maintenance and resulting investments. It is similar to any other equipment. For example, if you are driving a car every day, like 100 or 200 kilometers a day, it would need more servicing daily or regularly. Yeah, and the car will also become old very fast. But if you can control the demand, if you can only drive 50 kilometers a day, you can extend the lifetime of that vehicle. So, same logic applies here as well. It can increase network life and further increase reliability. It would also help to postpone infrastructure upgrades. So, because the service interval is long, the lifetime of that infrastructure can increase. Here you can see on the top left static pricing techniques and on the right side dynamic pricing techniques. So, this is the basis of demand response. This is how demand response works. So, within the static pricing you could have flat tiered pricing mechanism or time of use type of mechanism. Flat tiered means there is specific amount of the price of electricity varies at different tiers. So, you use this much, it will be cost you this much. If you use more, it will cost you more. Critical peak pricing. This means pricing of electricity at a peak time. So, that could be different. And then finally, to the extreme right end is real time pricing. Real time pricing is where pricing can change every minute, every second or accordingly. So, behavior change reducing energy use through reduction strategies, moving energy use to a different period and on-site renewable energy. Using on-site renewable energy. These are some of the ways in which you can bring about a behavior change. And this is an example of some of those. We will discuss these in more detail, these different approaches in more detail in the coming slides. From the utilities perspective, what are the different types of customers? Yeah. So, we have commercial customers, industrial, residential and electric vehicles. So, all these 4 different types of customers have different characteristics. They have different demand requirements, they have different time in which their demand is high. So, the peak time can vary for these different types of customers. So, one thing that you could think of from a research perspective now I am speaking, could you design a system that optimizes the consumption across all these 4 customer types? Yeah, because like I said, all the 4 customers have different characteristics. Their peak usage can be at different times. So, could you use that knowledge to develop a innovative system to address the energy, address optimal use of energy? So, within the demand response programs, you can find 3 different types of 3 different categories of demand response programs. So, let us look at the first option, which is called price options. So, here we have time of use rates. Here rates with fixed price blocks that differ by time of day. So, this type of a program, you will have a price for electricity, it will vary at different times of the day. So, in the morning it will be different, in the afternoon, in the evening and in the night you could have different rates of electricity, and that is why it is called time of use. So, at what time you are using the electricity, that time there will be a rate that is payable. Let us look at the next one, critical peak pricing or CPP. Here rates that include a pre-specified extra high rate that is triggered by the utility and is in effect for a limited number of hours. Yes, it is not going to last forever, it is only going to remain in action for a limited time during which, for example, the peak period. So, that is CPP, critical peak pricing. RTP is real time pricing. Here rates will vary continually in response to wholesale market prices. So, what we are seeing here is the rate at which the pricing changes is even faster. So here it may be, like I said, one day could be divided in 6 blocks of 4 hours each, just as an example. Here it only applies during a few during the peak period, so not across the other times, and this then goes to typically hourly rate. So you will have 24 different rates for a day. Yeah, so each hour you will have a specific energy rate. Similarly, there are some other examples like peak load pricing, peak day rebates, peak time rebates, Vickery-Clark-Groves approach, and so on. I will not go into details of this, but these are variations of price based demand response programs. Now let us look at incentive or event based options or event based programs. One of the first one here is direct load control. So in this approach, customers will receive incentive payments for allowing the utility a degree of control over certain equipments. What that means is utility can actually switch on or switch off some of your appliances. In the first slide, I showed you an example of clothes dryer with a DLC unit installed on it. So DLC is direct load control. So what happens is, if the utility realizes that the consumption is significantly higher and it cannot meet the demand, it will invoke its DLC functionality and could switch off high consuming devices such as washing machines, air conditioning units, or whatever. Yeah? And in return of that, the customers will receive incentive payments. So customer is also happy and the utility is also happy, because the system, the overall network remains alive, remains active. Thus reliability does not degrade. Next one we have is emergency demand response programs. Here customer receive incentive payments for load reductions when needed to ensure reliability. So what is the difference between the two? In one, the utility actually goes and switches off your machines. In the second one, the utility gives you the option to switch off. So you have to then go and switch off the machine yourself. And once that is done, the utility realizes that the load has gone down and appropriately provides you some incentives. Capacity market programs. Customer receive incentive payments for providing load reductions as substitutes for system capacity. So this is another version of the same. Basically, supply is less than demand. So we have to somehow manage supply with demand. So this kind of thing is within capacity market programs. Interruptible or curtailable program. So what is here? Customers receive a discounted rate for agreeing to reduce load on request. So here they are specifically saying that we will provide set amount of discount. Yeah, so that is interruptible. And similarly ancillary service programs as well. Next one in this category is demand reduction bids. So demand bidding or buyback programs, here customers are offered bid to curtail load when wholesale market prices are high. I think yesterday I discussed about auctioning. I don't know whether it was in the lecture or the tutorial, but when there is a particular product or service on offer and you can it is on auction, you can bid for that, and if you win, then you will receive that product. Same logic applies in this case. So here what we are bidding for? We are bidding for reducing the load, curtail the load. So if the utility company asks who is there who can reduce their consumption by X amount in the next 2 hours, probably 100, 200,000 or 1 lakh customers will say yes, I can do it. Then the utility company will choose who it will select from that group. So, that is an example of auctioning style approach. DR classification, demand response classification. Here we have task scheduling and energy management. So, within task scheduling, there is the control of activation time of the requested load. So, we are trying to see if we can schedule some loads at a later time or at a later day. Energy management, this reduces the power consumption of specific loads so that the total power consumption in peak demand hour is reduced. So, if you see in this figure here, is requested demand and compressed demand. So, here the air conditioning is on, the temperature is nice. When the air conditioning is switched off upon such a request, the temperature then goes up. So, it is showing you graphically an example of how demand response operates. DR programs can also be classified based upon a number of different classification criteria. So, you can see some of these criteria here, and each of these criteria can have multiple sub dualities. For example, the purpose of what could be the purpose of a demand response program? It could be reliability or it could be economics, means reliability, or it could be about profit. What is the trigger? It could be an emergency or it could be price related. What is the origin? It could be system led or market led. Motivation method for customer behavior change could be incentive based, could be time based. So, you can, there are many such criteria using which you can analyze demand response programs. And more information on this you can get from these papers here. These are very good papers to read for further information. So, now I will talk about the DLC, direct load control, and indirect load control. Indirect load control refers to incentive pricing, and DLC refers to when the utility interferes directly. So, what is the difference? Utility in the DLC, utility provider controls the load by remotely turning off the load whenever needed. So, consumption can come down, but this requires DLC switches to be installed. Yeah, how would the utility provider otherwise come and switch off appliances from your home? It will not be possible unless each and every appliance or high consuming appliance is plugged via a DLC switch. Only then a command can come from the utility center and can switch off that device. It requires maintenance. What is the main idea? To reduce load at peak time. So, here you can see some examples of load control switches. So, DLC controllers and some product details which I found on the internet. So, basically this DLC switch provides the utility with some level of control that they can exert when managing peak time demand. Compared to DLC, we then have incentive based pricing programs. So, how is it different than DLC? Incentive pricing does not directly control load as in DLC, because there is no DLC switch installed within the within the premises. However, it informs customers of different prices. What is going to be the price at a particular time, and with the objective to change user behavior by informing this pricing change. Users will use electricity when it is cheaper if they can do so. So, some activities which can be rescheduled during the cheaper time, customers can bring about that change using this approach. Here users are involved in load management. Yeah, so they become part of the overall equation of peak time load management. It empowers users and involves users in decision making. So, instead of utility switching off the device, the customer takes that decision, because sometimes if you switch off the machine directly using the DLC, it might also affect the machine, because if directly switch off. But if you properly switch it off, maybe press the pause button or hibernate mode or something like that, the machine is also not adversely affected. So, this refers to time of use concept. So, you could have peak time when the price is the highest, you could have mid peak where the price is medium, and you could have off peak when the price is the lowest. So, those activities that can be done during off peak, it makes sense to do it at that time, because the same activity can be completed for a very less amount, less cost. Okay, I have some questions here, but I think what we will do is we might do these in the tutorial. So, I will continue with the presentation now. Now, let us look into the communication requirements. Yesterday, the day before, we talked about overall communication within the whole smart grid context, and we identified a number of requirements. Some of them do apply in this context in the demand response program as well, because that demand response, which is part of AMI, is a subset, is one of the components of overall smart grid. So, we have to ensure quality of service. Quality of service means the system should be up all the time, it should be reliable, interoperable. Different types of devices and different types of DLC or different types of devices should be able to interoperate with each other. It should be scalable, flexible and secure. I think we went into these in detail during the session 3. So, I will not go into much detail here. However, what is interesting here is how you can bring about the change in the user behavior. Although we can say that if we notify the customer of a different pricing, that will bring about a change, but sometimes people might be busy in their day-to-day work. They may not realize that the price of electricity has changed at this moment, or it is going to change in the future in the next hour or so. So, to address that, there are some ways to inform users, to get them to know about it. You could send them an email, SMS, you could update it on the utilities website that the price change is going to happen. You could have a smart meter that automatically understands and configures the other devices or home automation system, or the end customer can receive a phone call. So, these are some of the ways of informing users, but all these ways also have the problem of time. I mean, somebody has to do all these things. Another thing that was proposed or was put in action was this energy orb. You can see this thing here. So, this is just a visual display of different times. So, when this thing is green, it means it is off peak. When it is yellow, it means it is mid peak. When it changes to red color, it means it's a peak time. So, if you have just like small thing, probably like a small cricket ball, put it somewhere in the living area, and it can give you easy indicator that what is the pricing at the moment. Is this an effective approach? Yes and no. And why? Because although you have this or although you have this, all these things, people have to make some decision in the end. Sometimes people are busy with their own work, and this could be one additional task for them to do. Some people might feel it is a complex decision making process. Others may think it is too much information to process. The frequency at which this changes, I mean, if this keeps changing every 15 minutes, then it's no point, so things like that. And finally, people are always not around. because people may be at work, they might switch on their washing machine and then leave for work. In that case, what will you do? So there is other things, that devices like this that is showing you how much energy you are using and how much does it cost. How much is it costing you right that moment when you are looking at it. You know, if there is a price sticker that is going up 16, 17, 18, 19, 20, you see that money is going out of your pocket, you know, then you might go around and see what you can switch off or what you can stop, and that kind of thing slowly brings about a change in human behavior. You can also get apps like this in which you can see the same information but on your phone. Coming to the benefits of demand response, I think we discussed it already quite a few times, but I would like to reiterate it here, that it helps in reduction in energy bills, offers higher reliability to the energy grid, several choices for customers to manage energy costs, improves overall system security and contingency, and improves market performance and competition. So there is benefits not only for the utility provider but also for the end customer, end consumer. So it is, which is why it offers a win-win situation in both the contexts. Another way of looking at it, at these benefits, is if you look it from the perspective of different stakeholders. So how do the transmission and distribution companies benefit, generation companies benefit, retailing, and finally the end consumer. So from the transmission and distribution companies, it relieves congestion, avoids outages, reduces overall losses, facilitates streamlined technical operation, and so on. From the expansion perspective, what is the benefit of this? It will defer investment, because you can use the existing infrastructure for a longer time with less maintenance, so cost comes down. From the generation perspective, on the expansion front, again you can avoid investment in peaking units. Like if you remember, I mentioned that 10% of infrastructure investment is only used for 1% of time, 1% of the peak time, because that's when you have no other choice but you have to rely on your generation facilities to just meet that 1% demand, and for that the investment is worth 10% in infrastructure. From the customer perspective, consumers are aware of the cost and consumption and even environmental impacts. Sometimes these devices that I showed you in the previous slides, they can also show you the amount of emissions that are generated because of you. Yeah. So you use this much of energy, how much emissions did it result? So they give you a graphical representation of that information, which adds context. So you realize, oh, because I switched on this much amount of emissions have happened. And to cover that much emissions, how many trees should have to be planted to convert that carbon dioxide to oxygen. So you know, that kind of information is what is going to bring about the cultural shift or change within human consumption patterns. Energy consumption scheduling or automated energy consumption scheduling is easy for users because it offers a set and forget approach. What does automated energy consumption scheduling means? If I were to say that I would like to limit my monthly electricity bill to a certain amount, say 1000 rupees or 2000 rupees is my budget, I could put that as one of the input to a home automation or home management system, and that system would keep tab of my consumption. If it realizes, so 2000 rupees monthly budget can be cut down into $500 rupees weekly budget. 500 weekly budget could be cut down to maybe 100 something or $80 rupees daily budget. So you can come down to a daily budget, and based upon the daily budget you can see what is it that you can afford to run in your house. Yeah, and then you will realize whether your budget is realistic or not. And one way to do is maybe first month just run and check your history. So you will realize how much you use and what time of the day you use, which day you are using. You can use that information then to budget. Then you can bring about a change in your lifestyle and limit within your budget. So this automated energy consumption scheduling is easy because it removes that decision making process takes the decision making process away from the humans, from the consumers. So you set a value and then forget about it, and then the system will take care of the rest. But what would happen in this situation? If you realize, or if the system realizes that you are going above your allocated budget for a particular day or for a particular hour, it could give you some notification that you are going to go over today's budget. So it will not stop the system, maybe it will not take actions unless it has been advised to do so in the policies that you implement within this system. But it can say, okay, today you are gone up over by 5% or 10% of your consumption. Make sure that tomorrow you cut down somewhere, yeah, so that you are within your budget. So such systems are policy based. Like I mentioned, you have to put some policies in place that would help this system to stick to budget. Yeah, so policy could be air conditioning can be switched off if I am going over my budget, or washing machines could be used in the evening when the cost of electricity is less, or something like that, some kind of policies like this. These policies are very effective because they are some way controlling your behavior of consumption, and they are self-learning. This system can learn your behavior and then even make you some recommendation. So you can see recommendation based research is also possible within the context of smart grid. What kind of recommendation the system could make? The system could look at your behavior and say that you can cut down your consumption by doing this, this and this, or you can swap these activities during off peak time or mid peak time, or things like that. So that those kinds of recommendations are possible. To make sure this is realized, you have to have ECS compatible devices, which means if your ECS system is going to require the ability to control your devices, then your devices should have that capability. Yeah, if the ECS has to switch off your air conditioning, it should have some way to do that. So the devices that you will use in conjunction with energy consumption scheduling, they should be compatible, easy to use, should be DIY, and should reduce users' electricity bill. In the end, that is what everyone wants. They want to make sure that their electricity bills are not very high. Okay. What time is it? Do you want to continue the next session, or we should take a break now and do on the next session later? Take a break? Okay. Alright, so we'll take a break now and then we can continue the second session after this. So here I will be talking about technologies for demand response, what technologies we can use, different types of monitoring systems, communication systems, optimization and load forecasting. So within the smart grid, smart technologies for demand response, it can include number of devices or options to realize this. This would include devices for demand reduction strategies. We discussed one example was the DLC. Communication technologies to monitor actual energy usage pattern. We saw the example using a mobile phone app, or also the device, electrical device on the that shows the prices. Communication devices to inform customer about events. That was an example of that round orb that I showed, which changes the color depending upon the time and the event of the price of the day at that time. Energy management tools and techniques. These are a broader group of techniques approach. Either it can be used to fully automate the home or automate a building, or depending upon how far they go in terms of implementing it. Devices such as load controllers, we saw DLCs, specific devices that companies can use for controlling the overall load of the system. Building energy management controllers. So these building management controllers work on top of the home automation systems. So within your home, you may have one system that controls your home, and then that provides information to the building automation system. So the building, it becomes like an aggregator, and then the building can take overall action on top of how the what kind of reporting it gets from individual houses. Then we can have devices for load curtailment, is another version of DLCs. Additionally, we could have on-site generation equipment such as a backup generator or something of that sort, in which case, for example, sometimes the demand response price signal may be quite high, but there is some activities that you cannot stop, in which case this building management system or home automation systems could compare whether it is worth to pay the high price for demand response, for the price signal that we have received via demand response, or should we use our own backup generator and generate electricity for that time frame. Smart meters and smart thermostats are some other devices that form part of the smart grid or the AMI infrastructure. And automated response technologies like control devices, monitoring systems, communication systems, and so on. So there is a wide range of devices, systems, frameworks that work together in an objective to control the consumption, to bring down the peak time load on the grid. Control devices. So load control switches like DLCs we showed before remotely control specific loads. For example, in the case of industrial customers, it could be motors or could be compressors that use large amount of energy in a very short span, and if it is continuously being switched on, it draws a lot of energy from the grid. So we can control that. Smart thermostats can remotely control temperature rather than on and off mode. So DLC is an example where if your air conditioning like this is connected with a DLC, it could only switch on or switch off the air conditioning. But sometimes it might be better that instead of switching on or switching off, if you can increase the temperature of the air conditioner, which may still keep running but the compressor will be off, because at high temperature, instead of at 16 or 17 degrees, you can have it at 22 or 25 degrees, so it is still, the comfort level is not very bad, but it is still manageable. So that kind of functionality is offered via smart thermostats. So it gives you that additional level of configuration. Rather than just switch on and off, you can change the temperature. Such systems or devices could be stand-alone, or they could be integrated into an energy management system. Some devices like DLCs could work independently. So you connect few devices and you notify the utility provider, your electricity company, that these appliances are connected via a DLC. So they have a record of that, and each device will have like a specific identifier using which the utility can know that this identifier means washing machine, or this means air conditioner, or something like that, and that can be remotely switched on or off to stop the thing. Other option is it can be integrated in the overall home automation or energy management system. So that will have much more, it will be much more beneficial, because the energy management system works on a broader context rather than just individual appliance level. It works at an overall house level or at a building level. So it can take decisions on a much higher scale and considering the broader impact rather than just a small short-term narrow impact. Local generation units like generators could be used. Automated energy consumption reduction protocols or approaches can be implemented in EMS. So this is another example for your research. How could you develop something that assists in energy consumption reduction, that assists you in reducing consumption of your electricity? You have the necessary devices that can measure your consumption, but you have to build something much more smarter by using that information. So these devices act as sensors. They capture information and they provide you that information. But what do you want to do with that information later on? So you have to think about that, and that is where intelligence in smart grid exists at the application layer. So this is where I'm talking. If you remember the 5-layer architecture that we discussed few days ago, there was application, security, communication, control, and power. Those were the 5 different layers. So getting this information and developing intelligent algorithms from this sensor data will help you to implement a very effective energy management system, very effective EMS. In summertime, we spend a lot of energy for cooling, and lighting is always there. In the winter time, in the winter peak, we spend a lot of energy for heating. So there is seasonal variation in consumption patterns as well. How can we adjust temperature with minimal impact on comfort? This is again a question mark. Something that could be researched into. Another research question for you for your project maybe. Refrigeration, elevators, outdoor signages, etc. They are all huge consumers of electricity. So how could you prioritize which customers and which devices or appliances that these customers use in an overall framework for reducing electricity? Another thing for you to think into. Control devices, backup generators, industrial and commercial, now even residential. Many houses or colonies now have a big electricity generator within there. So in case there is power failure, the whole system has a backup. Same like the backups, the UPS you have in the computer labs here. But on a larger scale. The UPS there you have runs the computers. But it could also, if it is a large scale battery or storage system, it could run everything, almost everything that you have at home. By doing this, you can maintain your normal operations. However, the drawback is pollution. Many of these generators are either diesel powered or petrol based. So that causes a lot of air pollution. And if it should only be used in a case where either the price signals are just too high and you cannot afford them, and the cost of the price signal versus the cost of using the generators, if the generator is better, then you would switch to that option. Coordinated consumption, buildings or tenants, different departments within an industry. we discussed about coordinated consumption for electric vehicles. Remember, one of the papers that we were discussing during the tutorial was electric charging and discharging of electric vehicles in a coordinated manner. So same logic can be applied for individual houses or tenants or buildings or within different departments within an industry. Basically what we want to the peak period, we have to shave the peak. We have to make sure that the peak is as much, we can flatten it as much as possible. So example of coordinated consumption could be, instead of every company starting at 9 o'clock or 10 o'clock, they could shift it over a few hours. Some start at 8 o'clock, some start at 9 o'clock, some start at 10 o'clock. Yeah, so that will bring about a change within the energy consumption pattern. It will also have impact on the traffic on road. Not everyone will leave their home at 8 o'clock to be in office at 9 o'clock. Some may leave at 7 to be there at 8. Some will leave at 8 to be there at 9, and so on. So it will have follow-on effects as well. So that is what we refer here as coordinated consumption. Another topic for you to research here: energy storage devices, off-peak energy collection and charging of electric vehicles. So we have options like we discussed before. Electric vehicles can be used as a storage. They could be charged during the off-peak time, can be used during the peak time. Within the monitoring systems context, we have smart meters, which we discussed, advanced metering infrastructure, which is the overall backbone of smart grids. We then have energy management systems, which work at a smaller scale, and we have energy information systems, which work at a larger scale. So we will go through them. So smart meters I will skip. Okay, AMI, advanced metering infrastructure. So this is composed of wide area networks or WANs, home or local area networks or HANs, meter data management systems MDMS, operational gateways, systems for integration into software applications, and neighborhood area networks. So it is basically an hierarchy. You start from the home, so the network of your devices within your home forms the part of your home area network. You then have neighborhood area networks, which means your neighbor, neighbor's neighbor, a collection of houses or buildings within one neighborhood. Then a collection of NANs represents a wide area network, so it's even bigger. So you can see how the network starts from one house and then gradually becomes bigger and more complex. So within that you have meter data management system. So all these hands here will at least have one electricity meter. Yeah, each home will have one meter. So all these data that comes from the meter has to be somehow managed. So you have a system for that, which is called the meter data management system. Then all the data other than the meter data, all the price signals, any kind of a data that is generated throughout this system is then managed, has to be managed from the perspective of integration and into data integration and into a high level software platform. So when we are talking about high level software platform, it is the application layer that we discussed, the application layer, the top layer in the smart grid architecture. So this figure here gives you a good idea. We start at home networks. We have smart meters for each home. All the different homes form a part of the neighborhood area networks. Neighborhood area networks connect with the wide area networks using edge routers or collectors. These routers or collectors gather information from individual neighborhood and send it over to the utility or wide area network. On the wide area network you will have the application level, the application level software or the data analytics, all that happens all up at this level here. So all the intelligence flows from bottom to top, and the data that is needed to derive that intelligence flows from bottom to the intelligence flows from top to bottom. The data from the sensors flows from bottom to top. Energy management systems, or EMS, they are designed to improve buildings' energy performance, to save energy, to reduce peak demand, and to carry out automated demand response programs. So whenever a signal comes from the utility for a price variation, that signal goes into your EMS, goes into your software, and then that software will take relevant action based upon the policies that are implemented in that software. So the policy could be, if the price signal is above a certain threshold, then cut down your consumption. If the price is between this and this, you can continue with your existing consumption, and something like that. So whatever price signal comes, there will be a policy reflecting that price signal. It will also have the facility for monitoring, analyzing and controlling. Sensors, routers, switches and actuators form integral part of your home automation system, because action has to be taken, not just information. This also represents a vast array of control systems and numerous intelligent and innovative algorithms that can be implemented at each and every stage within this whole smart grid context. For example, for monitoring, you could implement load control strategies, measurements in 1 minute intervals, verification of control response from the customer back to the utility, measurements in 1 to 10 minute intervals, development, updating of load models, and so on. So there are a lot of things that happen when you are part of a smart grid. Okay, on top of the EMS is EIS. So this is a much broader and much more complex system. Basically, it deals with information gathering from all the different sources that are reporting to it. So it operates as a gateway between a utility and existing EMS. So in the previous picture here, it will be somewhere at this level. The EIS will be at this level, EMS will be at this level. EIS uses the energy information and uses that for load management. It collects system performance data for users and utilities for use in building operations, billing analysis, reporting, receiving DR alerts, and so on. So that whatever activities happen within the smart grid, this will be a top-down flow. So the intelligence for gathering energy information or for load management will be processed at this level. All the analysis, all the analytics, everything happens at the EIS level, and from EIS, the downstream response that goes via the AMI framework through the demand response approach is this, so that at the end user where the EMS is implemented, they can take respective corrective actions to ensure that the stability and the reliability of the system is not compromised. Automated response capabilities, where notifications could be sent to the users or users could notify to the utility based upon policies. Communication systems in the context of demand response are required for implementing DR programs, because market and emergency signals have to be delivered via the AMI infrastructure. In lecture 3 we discussed about communication. So in that lecture you understood a lot of options, a lot of communication requirements, probably 12 or 15 different dimensions of communication we studied in that lecture. So why is that very critical? Because the utility or the electric company has to provide you with the pricing signals for each and every day. And that communication, that system has to be reliable, has to be secure, has to be scalable, and it has to work, in other words. So you could have one-way communication which can be simple and cheap, where we can alert customers about DR events, no monitoring or verification if customers reacted to the event. So you can have a one-way communication, but what we actually want is a two-way communication. So two-way communication, the challenges is very expensive, as they are very high upfront costs. Customers can respond back using the same communication medium. They could report load back to the utilities, how much load they are consuming, or how much is the load that they are expected to consume at a later day. And this all information can be stored via different policies within your EMS framework. And it is the most appropriate way for realization of smart grids, because in a smart grid we definitely want two-way communications to happen. We don't want just one-way communication, because that interplay between the consumer and the utility grid is what makes this kind of a system more valuable. So what is the importance of such systems? They can monitor available facilities during a DR event, assist in knowing diversity of loads, whether it is going to be industrial loads, it is going to be commercial load or residential. Accurate monitoring and verification post DR request. So what may happen once the utility sends through a price signal that the price is going to go up or price is going to go down, the utility in the end has to know whether customers have taken some action after that request. Yes, so that is monitoring and verification. That is what we are talking about here. So the utility should have have a way in which it could monitor whether customers have taken action against what was requested. And a two-way communication is the only way that this is possible. Measure individual customers' load reduction. So previously we discussed about different types of demand response programs. So there were incentive based programs, there were price based programs, and there were auction based programs. Yeah. So for the electricity company, the utility, it has to know whether the customers have actually reduced their consumption, and if they have done so, that information has to be reported back to the utility, because it helps in easier billing and it streamlines incentive payments. So if customers did what they were told to do, that is to cut down their consumption, and if they did consistently, it is easier for the electricity company to record that information and then to provide whatever incentives that were agreed upon before entering into this DR arrangement. HANs, smart meters, communication gateways, NANs, data connectors, WANs, central control centers, etc. These are all required for different communication technologies for the realization within smart grids. We just saw in the previous slide how the hierarchy from the very bottom and going up the way all to the top, the level of communication that is necessary and the devices that are used in that communication. So these devices could be wired like PLC or fiber optics, or it could be wireless, such as ZigBee, Wi-Fi, GPRS, LTE, WiMAX, and so on. Within the DR optimization, we have to think about what is the optimization objective. What do we want when we say optimization of demand? What is it that we are actually talking about? So what we want to achieve by optimization is minimization of total power consumption and or maximization of social welfare. So that is our optimization objective. Whenever you are going to optimize a system, it has to have a few optimization objectives, and against that optimization objectives you will optimize your system, and then you will measure whether your system has optimized or whether it has realized its optimization objectives or not. So in case of this, these are the two objectives: minimization of power consumption and maximization of social benefit or social welfare. So what is the problem now? We want to find a set of variables that minimizes or maximizes a certain function. So in this case, we want to minimize total power function of this set of variables, while these variables subject to a set of constraints. So what could be the constraints? In this constraint, one of the constraint is the maximum amount of capacity for the power station. Variables: demand, request, start time, operational time of the load, and type of load. Some examples of types of variables you might have to work with when you are optimizing the system. Function, which was here, total power consumption or social welfare. So that is the function that we want to optimize the system against. Constraints: capacity of the generator, energy storage, and appliances. So if you look at these three at the bottom, variables and constraints. So we have to work with these three sets of information to achieve these two objectives. Yeah, so there are already many different types of optimization algorithms, optimization approaches proposed in the literature. You can study them and you can see how effective that optimization is. And there are many different ways of optimization as well. I think the next slide will talk about, here you can see many different methods, optimization methods, like stochastic optimization, particles PSO, game theory, robust optimization. We discussed some of this yesterday or day before. And optimization targets could also be different. Yeah, in the previous slide we just saw examples of two different optimization approaches, objectives. There could be other objectives, such as we want to minimize cost, we want to maximize welfare, we want to minimize consumption, we want to minimize cost and minimize consumption, we want to maximize welfare and minimize cost. So there could be a permutation and combination of all different options that you have. And when you have permutation and combination, it increases your the problem complexity. And you can see, study these different methods to solve these problems. Yeah, it could be one method, it could be a mix of, it could be a hybrid method. Okay, next, load forecasting. Load forecasting has to be based on a horizon. That is, are we forecasting for weekly demand, daily demand, or hourly demand? So that is the horizon. We can have three horizons, or it could be even daily, or it could even be hourly. So when we are developing a load forecasting algorithm, we have to keep this in mind. So very short term load forecasting is called as VSTLF. It could be at the granularity of minutes or hours. So TLF. STLF could be at days level, at the horizon is days here. MTLF is weeks, and long term is at months or years. So to do this forecasting at these levels, you need to have access to required information, and the quality of that information or quality of that data has to be relatively as precise as possible, because these forecasting algorithms would rely on that information heavily. So what is information that we need? We could need electric load parameters such as load profile, aggregated load profile, and so on. We could have weather parameters such as temperature, solar radiation, because different times of the day and different days of the season, the weather is different, and the renewable sources, how they perform, will be different. We also need to know the economic and demographic parameters. People living in the rich suburbs, rich areas, will have a different demand profile compared to people living in a poorer suburbs, poorer areas. They will have a different demand profile. So that is also has to be accounted for. Regional development of the country. Is it a highly developed area, or is it still developing? because highly developed versus developing will have different characteristics. Maybe the load characteristics will differ. Devices that are used in these areas or these types of states or cities will be different. Domestic sales of HVAC units. So if you have this information, you would know how many air conditioning or heating devices are installed in my city. Yeah, because if I'm thinking from a perspective of a utility provider, as an electricity company, if I have all this information, I will be in a much better position to make a very realistic load forecasting. Yeah, this is just a starting point, just a sample, just to tell you this information can be used, but other than this there is a lot of other information, and the more information that you can have, the more reliable your model is going to be. So in forecasting, you could forecast, there are different types of forecastings that you can do. You could forecast one value, or you could forecast multiple values. Yeah, so there will be algorithms for doing one value forecasting, there could be algorithms for multi-value forecasting. So let's look at some examples of in the first category. Next hour's load is, we are just calculating, forecasting one item. What is going to be the load for the next hour? What another example is next day's peak load. So how much load can we expect tomorrow in that time frame? What could be the next day's total load? Yeah, so you can see that these examples are, we are only forecasting one thing, one item. Yeah, and you could run forecasting algorithms to calculate different types of these items. Forecasting multiple values. So here you could have forecast for next hours. Instead of 1 hour, you could have it for multiple hours. Peak load plus other parameters. Next day's hourly forecast. So we are increasing the horizon when we are going for multi-value forecasting. And some examples of methods that you can use here are ANN, self-organizing maps, SOM, or neural gas networks, and so on. Similar to load forecasting, you can apply the same concepts, same methods, same tools, same algorithms for doing price forecasting. Yeah, because the electricity company has to send the price information as well. So it is not just the demand, but they have to predict what is the pricing. And why is it important? Because it is very critical. If the pricing goes very wrong, which means if the pricing algorithm comes out and says that the peak hour pricing is going to be this many rupees, and suddenly people think that, oh, it's a very good value, yeah, and everyone starts using, everyone starts consuming even at the peak period. So that worsens the problem. If you look at here, there was one thing I mentioned, economic and demographic parameters. So it applies in this case. So when you're forecasting something, you know the buying power of your target customers. If you want to restrict the consumption in peak period, you need to know how much people can afford to spend. If you have that demographic information, your pricing algorithms would work more effectively, because you know whether they can afford or not. If your pricing algorithms come up with a figure that almost everyone can afford in the peak period, you are going to be in trouble, yeah, because the peak demand is not going to be reduced. So electricity prices, they show strongly seasonal nature, they are price dependent, and there is a correlation between electricity price and load. So some things that you can incorporate while developing pricing algorithms. Like here, we had so many parameters for load forecasting. Similarly, you would have a lot more numbers for price forecasting. So the inputs to any of these approaches vary a lot. And these methods, these forecasting algorithms can also learn from the past. Yeah, so if, for example, if you make a mistake or your pricing algorithm does not provide you very good pricing in one time, next time it can improve from that knowledge, and some of these things can also be automated. Okay, so that concludes today's session. In conclusion, what is the takeaway from this session today? You learned what demand response programs are, the different types of programs, price based, incentive based, auction based, what different types of customers are, industrial customers, commercial, residential, retail. We then looked at the benefits of demand response, energy consumption scheduling, why it is important and how it can be realized, the different technologies we can use for demand response, importance of monitoring, communication and optimization, and also load forecasting and pricing. So what you see today, what we have covered broadly is within the context of demand response, a lot of things are happening. Demand response is not as simple as electricity company, utility sending a price signal and managing the demand. It is not that easy. There are a lot of things that go underneath. A lot of things are happening within that. So demand forecasting the load is one of that. Load forecasting is directly related to your pricing. So if your pricing models work properly, you will be able to manage the load correctly. If the load is not managed correctly or the pricing is not correct, it will instabilize your network and so on. We also looked at the number of different types of inputs that you would need for these prediction and forecasting algorithms. The more values you have, the more data you have, and the quality of that data that you have will play a very important and a significant role in how eventually your system performs. The outcome of the system heavily depends upon the quality of information, not just information, but the quality of that information. Okay, so we'll conclude our session today on this topic, and we will start our tutorial shortly. Okay, thank you very much.